Okay, hi everyone. So the lesson that we just had was on basic trig equations, and this lesson is on more trig equations, so they're just getting a little more complicated. So more solving of things and trying to solve for theta and figuring out how do we write the solution set in the correct way. Okay, let's go ahead and get started. So really, because this is just more trigonometric equations, we probably could have just merged these two sections together and made it one section. But I think it would be a little bit of a long section. It might be overwhelming if we did that. So we separate it. Gave you some time to digest the other one. And now we're ready for this. For complicated trig equations, we might be able to rewrite first using trig identities. And then solve. So that's one type of problem. That's one type of problem we need to address. You know that earlier, not too long ago, but a few lessons ago, we used trig identities to simplify things. And then in the previous lesson, we solved for all solutions of a trig equation. And now we're combining both ideas. The idea that trig identities can simplify expressions and the idea that we can solve trig equations. I'll show you an example. Let's say we want to solve 2 cosine squared theta plus sine theta equals 1. So I'm going to talk us through this one. What's different about this one compared to the previous lesson is that this equation involves two different trig functions, and I don't think we saw that in the previous lesson. This has sine and cosine. One of them is squared and one of them is not. So the suggestion is, I don't think there's any algebra that we could jump into right away, but maybe there's a trig identity that could help us rewrite this. I feel like it would be helpful if we could get this all in terms of one trig function, either cosine or sine. So here's an idea. Let's use, this is the most commonly used trig identity in this course, I guess. This one, right? Sine squared plus cosine squared equals 1. What if you solved for cosine squared theta? You get 1 minus sine squared theta. So the problem becomes, we can rewrite this as 2 times 1 minus sine squared theta plus sine theta equals 1. So we accomplished my initial goal of trying to get this problem to be all in terms of one type of trig function. Now it's just in terms of sine. I think that that's going to be more helpful, even though one of them is still squared and one of them is not, so that's something we have to figure out. I think this is better. Let's distribute the 2. Let's see what happens. Distribute the 2. Okay, that's where we're at. All right, so we had something kind of like this in the previous lesson. This is one of these ones that kind of resembles a polynomial. So how about this? Let's rewrite it as negative 2 sine squared theta plus sine theta. Let's combine, let's bring this 1 over, right? Subtract 1 from both sides so that we can merge it with the 2. So the 2 becomes a 1. We get the right-hand side to be 0. This is one of those things that resembles a polynomial, even though it's not a polynomial. And then thinking about maybe, like, is there some factoring we can do? I think something that would help is if we multiplied both sides by negative 1. I'm going to flip the signs. All right. So at this point, I'll say scratch work or side note, whatever you want to think of this as. I feel like this resembles the polynomial 2x squared minus x minus 1 equals 0. And if you gave me this polynomial and asked me to solve for x, I would factor it. I would try to factor it. If it doesn't factor, I would use the quadratic formula. But I think in this section, things will factor. Factoring's always a little trickier when there's a 2 out front. You know that this has to be 2x and this is going to be x. And then figuring out what numbers go in here. Well, luckily, this is a -1 out on the right side. So whatever numbers I put here, if they're going to be integers, they have to be integers that multiply out to -1. There's not that many choices. It's either going to be +1 -1 or -1 +1. And then you figure out which one of those two options works. It's +1 -1. So I'll put that in parentheses and say what that tells me is that this problem factors to 2 sine theta plus 1 and then sine theta minus 1. This leads us on 2 different paths. This one says that 2 sine theta plus 1 equals 0, and this says sine theta minus 1 equals 0. So we might be getting solutions from both of these paths, but don't forget last time we had a problem where like one of the directions had no solutions. That happened in the previous lesson. But okay, so this, subtract 1 from both sides, divide 2 from both sides, so you get sine of theta equals -1/2. I think that does have solutions. It looks fine. And this one over here says sine of theta equals 1, and that also looks like it does have solutions. So the way that we've been solving this is we often think about the unit circle. We think, where on the unit circle does this happen? Sine of theta equals -1/2. It's going to happen here and here. Where on the unit circle does this happen? It's going to happen up here. So when we look at the unit circle to try to find some solutions, what we're really doing is we're finding solutions in the first period. So this one we just found is pi over 2, and that's in the first period, meaning it's in that interval we talked about at the end of the last lesson, where this is the solution in this interval. And over here we found 2 solutions in that interval, didn't we? We just found 7 pi over 6 and 11 pi over 6. And these are both in that interval. However, remember, this problem, at the beginning of this problem, it said solve. It didn't say to find just the solutions in that interval. It said solve. When a problem says solve, it means it wants all solutions. The ones that are in the first period and all the others that you get from doing plus 2k pi. So we're going to say we got 3 different types of solutions. And you could list these in any order, but there's this one plus 2k pi. This one plus 2k pi. And this one plus 2k pi. In order to truly be talking about all possible solutions, where k is any integer. So that's the answer. Whoops, I'm at the bottom of the screen there. There we go. So, this was using some of the things we talked about in the previous lesson. It's one of those ones that we had to use factoring. But the part about this problem that was new was just this first part, really. the first part where we said, wait a second, there's a cosine and a sine. I'd like this to be in terms of just one trig function. So we used this, and we got to rewrite it just in terms of sine. Now, I'll tell you that there's probably other ways to do this as well, using trig identities. You could probably find a way to rewrite this entirely in terms of cosine by changing sine around somehow. If you did that, you should still get the same answer. I think the way that we did it here seemed like the natural way to do it, in my opinion. Now, the trig identity that we used on this problem, sine squared plus cosine squared equals 1, and then we rearranged it, that's not the only trig identity that you can use. We have a whole reference sheet of trig identities, and maybe there's a problem where a different one will help. That's kind of a hint, because I'm about to give you a problem to try. And maybe there's a different trig identity that will help with this one. So I'd like you to try to solve sine of 2 theta minus cosine of theta equals 0. So you can pause the video and give that a try. So I think, and remember, there might be more than one way to do this, but I think that the most useful trig identity here is going to be something that addresses the sine of 2 theta. I think we should use the double angle formula. There's a double angle formula for sine. It says sine of 2 theta equals 2 sine theta cosine theta. And, if you're looking at that reference sheet of trig identities, it probably has this with x's instead of thetas, but we understand that that's just a different labeling. It's the same thing. So the problem then is, the problem becomes, let's replace 2 sine theta with this. So we're replacing sine of 2 theta with 2 sine theta cosine theta. Okay. And now we need to continue solving this. All right, so do you know what to do next? Well, you should know what to do next because I cheated a little bit. Now, this is a problem. We solved in the previous lesson. So I'm not going to show all of the steps. You can refer to the previous lesson for that. And I'll show you the answers, though. Do you remember this one? I think this was one where I gave you a hint, and I suggested that you factor out cosine of theta. All right, so we get pi over 2 plus 2k pi. 3 pi over 2 plus 2k pi. Pi over 6 plus 2k pi. And 5 pi over 6 plus 2k pi. By the way, you know how in the previous video lesson I said that the where k is any integer, I said that it was optional whether you want to write those words or not, because it's kind of implied from context. Just as a little side thing, in case you're interested, there's another way to write this. In fact, if you want to kind of do something mathy and kind of cool, you could say this. This means where k is in the set of integers. The fancy-looking z is the set of all integers, and the little symbol here means, it's an element of. So where k is an element of the set of integers. That's a little bit quicker. In fact, you could even leave out the word where. You could just be like, write this and then say k is in the set of integers. That's pretty cool. Okay, so we've got some other problems to solve. This problem was interesting because of the sine of 2 theta. We didn't have any like that in the previous lesson. And in general, we want to talk about equations involving multiples of theta. We just did one, right? So I'll say for sine of 2 theta, we used the double angle formula. I think that made the most sense because it's a trig identity that's literally about sine of 2 theta. So let's use it. But what if we had a problem that had sine of 3 theta? Maybe not the exact same problem, but just some problem that involved sine of 3 theta. I'd like you to think about this. Can you think of, like, how would we even deal with that? I'm going to tell you 2 methods. So one idea is that we could use the addition formula, or the addition formula that goes sine of x plus y equals. So what it would look like is sine of 3 theta, you could rewrite it as sine of theta plus 2 theta. How about that? And then that becomes my x and y. Put it into the addition formula, it looks like this. Well, okay, but this is kind of messy because now instead of sine of 3 theta, now we have all of this. But it's like, what do we do about this? What do we do about this? So unfortunately, I would have to say then use the double angle formulas. For these parts. Well, I think I said that I was going to tell you 2 different methods. So this was one idea. But this is a lot of work, and there's a better way. So we're not going to actually do it this way, even though technically this is valid. You know, technically it would work, but there's an easier way. For problems involving something like sine of 3 theta, we can solve the equation for 3 theta instead of theta. Then adjust our answer accordingly. So it's going to add an extra step at the end of the problem where we have to adjust our answer, but this is going to be a lot easier than that other thing of trig identities. I'll show you what I mean by this. We'll do one with sine of 3 theta. So in this section and in the previous lesson, you know, all along we've been trying to solve for theta, and this idea is, well, just solve for 3 theta instead. So I'll show you this one. Let's solve 6 sine 3 theta minus 3 square root of 3 equals 0. It's the 3 theta that's got this, the 3 theta is what makes this one a little more complicated, and that's why it's in this lesson instead of the previous one. Okay, but first things first, we could do some basic steps on this, right? We could like rearrange it. Let's rearrange this to 6 sine 3 theta equals 3 square root of 3. We added that to both sides. And let's divide both sides by 6. What happens when you divide both sides by 6? Well, 3 over 6, this is going to be square root of 3 over 2. Okay, so that's simplified. That's equivalent to the original problem. If this right now said sine of theta equals square root of 3 over 2, then it would be just like a problem from the previous lesson. It would be in basic form. We could solve it, no problem. It's the 3 theta that we have to deal with. But for just a moment, let's think about places where does sine of something equal square root of 3 over 2. I know some places on the unit circle where sine of something equals square root of 3 over 2. I can think of 2 places. 2 of the common angles that we deal with. There's this one here, right? This one here. I guess this one is pi over 3. And this one is 2 pi over 3. If we went all the way to there. Let me zoom in on that. I just want to make sure you can see that. So yeah, I know 2 places, pi over 3 and 2 pi over 3, where sine of those angles equals square root of 3 over 2. But these are not values of theta, right? These are values of 3 theta. So 3 theta equals pi over 3. All right, we'll zoom out. And 3 theta equals 2 pi over 3. Those seem to be the answers in this interval from 0 to 2 pi. Those are the answers for 3 theta. But the original problem said solve. And when a problem says solve, they really want us to find the values of the variable. The variable in this equation is theta, so we need to adjust our answer accordingly. Okay? First, what we could say is we could write all solutions for 3 theta. It would be 3 theta equals pi over 3 plus 2k pi. 3 theta equals 2 pi over 3 plus 2k pi. Here, I'm going to do that thing where I say k is in the set of integers. That's pretty cool. Now we want... I'm not putting a box around that yet. We want to adjust these answers to get solutions for theta, not 3 theta. Well, what step do you think we would do to switch this from being solutions for 3 theta, and we now want them to be solutions for just theta? All we have to do is take the solutions and divide both sides by 3. From the solutions that we wrote. If you divide the left-hand side by 3, you get theta. That's good. What happens to the other side, though? Yeah, so you have to divide 3 into both sides. So like the pi over 3 plus 2k pi, that gets divided by 3. So the pi over 3 becomes pi over 9. And the 2k pi becomes 2k pi over 3. And similarly for the other one. Divide all terms by 3. This is going to be 2 pi over 9. And this is going to be plus 2k pi over 3. And that's the answer, where k is any integer. That's the solutions for the variable theta. So what do you think? Was this a hard problem? I mean, I don't think it's so bad. We didn't really have to use any trig identities. The way we did it was we basically had a problem involving like a multiple of theta, and this was 3 theta, but you could say, well, if the problem had been 4 theta or 5 theta, we could still do the same idea. So any multiple of the variable, and if it was cosine or whatever, you could still use the same idea. You solve for, in this case, 3 theta, and we found solutions for 3 theta in the first period. And then I went ahead and actually wrote out what would the solutions, like what would all solutions be for 3 theta. And it's important that you do this before you divide both sides by 3, because you need the 2k pi to also have a 3 on the bottom. Does that make sense? So I didn't just take pi over 3, 2 pi over 3. I didn't just divide those by 3 and then add 2k pi, because then I would have pi over 9 plus 2k pi, 2 pi over 9 plus 2k pi. Those would be wrong because they wouldn't have the 3's underneath. So write out the solution. My suggestion is write out the solutions for 3 theta and then divide all terms by 3. Or 4, or whatever it might be for the problem. Now, this discussion was about problems that have multiples of theta, and I used 3 theta as an example. I'm going to tell you that you can use a similar strategy for problems involving something like sine of theta over 2, cosine of theta over 3, etc. Those could also be considered multiples of theta. So you would basically, in this first one, you would solve for theta over 2, and then you would adjust your answer accordingly. In that case, you would probably get an answer and have to multiply the answer by 2. We could do a problem like this. Yeah, let's do a problem like this. Let's solve square root of 3 tangent theta over 2 minus 1 equals 0. I guess I'll do this one. I mean, if you want, we'll say if you want, you can pause and try this. But I was planning to talk us through this one. All right, definitely rearrange this first. Square root of 3 tangent theta over 2 equals 1. I brought the 1 over to the other side. And then I'm going to divide both sides by the square root of 3. So tangent theta over 2 equals 1 over square root of 3. Now, do we know any place on the unit circle where tangent is 1 over the square root of 3? We might not know like off the top of our heads, but I think we could figure it out. I think that the square root of 3 shows up in enough of these problems that we can figure this out. Let's do some work over here. I'm going to say that tangent of something is sine of something over cosine of something. So that's a good place to start. I want sine of something. I'm going to actually leave a little bit of space. Sine of something, cosine of something. I want it to equal 1 over the square root of 3. I don't think that there's going to be something where cosine of an angle equals the square root of 3, because that's bigger than 1. But I do know a place where I could get this to be the square root of 3 over 2. That's where the square root of 3 shows up the most, right? This number. What is cosine? Cosine of what equals this? How about pi over 6? Now, if I did the same angle for sine, what happens? Look at this. It works, doesn't it? This works because you get 1 over the square root of 3. So I kind of got to this by like reverse engineering it. Like I knew that I needed a square root of 3 to show up on the bottom. I said, well, how do I get a square root of 3 to pop out of cosine? It's probably going to be a square root of 3 over 2. So I tried this angle that has cosine of this is the square root of 3 over 2. And if I put the same angle in for sine, it just so happens that it works out. So the place on the unit circle that we're looking at, pi over 6, is about here. I also want to remind you, something that I said in the previous lesson is that tangent has period pi. All right, so remember with we did a problem last time, I think that was a cotangent problem. And I was saying that with most of the trig functions, we add 2k pi. But for tangent and cotangent, because their period is only pi, we have to add k pi. So what is one period of tangent? Well, let's just say we found solution for theta over 2 is theta over 2 equals pi over 6. And there's no other solutions in the first period of tangent. So all solutions for theta over 2 are theta over 2 equals pi over 6 plus k pi. And I'm only adding k pi, not 2k pi, because tangent has period pi. Now we need to adjust answer to get all solutions for theta. Well, I see how we're going to do that. We have solutions for theta over 2. Just multiply both sides by 2. So what happens when you multiply both sides by 2? This becomes pi over 3. This actually does become 2k pi, where k is an integer. To do this, we multiply both sides by 2. Cool, so that was good. That was a problem that involved tangent, which, you know, tangent and cotangent can always be tricky. And then it was also a problem that involved theta over 2, so I'm glad we did that. All right, I'll give you a problem to try. I'd like you to solve, and I'm not really telling you how to do this. No hints for this one, just you can figure this out based on what we've discussed so far. There might be more than one way to do it. All right, I'd like you to pause the video, take a couple of minutes, and try to solve this one. So I'll show you what I did. I saw a trig identity that I thought would be the most useful, and, you know, I mentioned that there might be more than one way to do this because there might be more than one trig identity that could help you rewrite this. But I thought, let's use cosine of 2 theta equals 2 cosine squared theta minus 1. And that's one of the double angle formulas. I mean, we used a double angle formula earlier today. So, yeah, I think with 2 theta, that's going to help. Also, look at that. It's going to turn it into cosine squared theta, and the problem already has a cosine squared theta. So I feel good about that. 2 cosine squared theta minus 1 equals cosine squared theta minus 1/2. Yeah, this is good. Look at this. Let's subtract cosine squared theta from both sides. We get cosine squared theta. At the same time, let's add 1 to both sides. You get 1/2. Look how much simpler that looks. So I think that's helpful. I think that's good. Cosine squared theta equals 1/2. So let's take the square root of both sides. But when we take the square root of both sides, it's going to be plus or minus the square root of 1/2. Do you know what the square root of 1/2 is? Or, yeah, square root of 1/2. Well, it's a number that when you multiply it by itself, it gets you 1/2. Let's work with this a little bit. Let's work with this. Because I'm thinking, like, do I know an angle that when I do cosine of it, I get this? I don't really recognize it in this form, so I'm going to rewrite it in another form. First of all, when you take a square root of a fraction, you take the square root of the top and the bottom. Well, the square root of 1 is 1. So that's a little bit better. And then that gives me the idea of when we see a square root in the denominator, we often multiply it by, multiply by square root of 2 over square root of 2, right? What's that going to turn this into? Well, we still have a plus or minus out front. The numerator turns into the square root of 2. The denominator, square root of 2 times itself, is 2. This looks more familiar to me. Now I think we can work with this. I need a new page because I'm near the bottom, but let's say that where we're at right now is we want cosine of theta equals plus or minus the square root of 2 over 2. We can do this. We can do this. I'm going to draw one unit circle and kind of address both the plus and the minus. So where do we know on the unit circle where cosine of something is going to be either the square root of 2 over 2 or the negative of that? It happens in 2 places each. So actually here, here, and these two. Cosine of any of those angles is going to give you either a square root of 2 over 2 or the negative of that. So all solutions. You know what? I think there's going to be a couple of different ways we could write this. Well, first of all, what are the angles that I have here? I guess I've got like pi over 4, 3 pi over 4. Let's add 2k pi to each of them. Um, 5 pi over 4 and 7 pi over 4. Do you see why I think there's a really good way we could rewrite this? Like a simplified way. Can we merge some of these together? Well, I mean, the first solution and the third solution are exactly pi apart from each other. So maybe we merge those two. Or we could say the second solution family and the fourth solution family, those are also pi apart from each other. So we could like merge those together. But actually I see another idea that the picture gives me an idea. How far apart are each of these? Like to go from here to here or here to here. They're all the same distance apart on the unit circle. It looks like it's like a plus pi over 2. So how about this? How about we take the first solution and I say I want to add any multiple of pi over 2. How do you want to write that? How about this? That looks pretty good. Where k is an integer. I think that's a nice simplified way of writing it. I guess you could do you could do k pi over 2 if you want. So let's just check. Does this work? Does this get us all of these solutions? K is any integer. What happens when k is 0? When k is 0, we get this. All right. When k is 1, we have pi over 4 plus pi over 2. That's going to get me this solution. When k equals 2, I'm actually adding pi. So that's going to be pi over 4 plus pi, which is going to be 5 pi over 4. What happens when k is 3? We're adding 3 halves of pi to pi over 4. That's actually going to get me 7 pi over 4. So this is kind of a cool compact way of writing all of these solutions. It's like 4 families of solutions that we've condensed into just describing it as one family of solutions. So I think I have one more problem. I'll do this next one. I want to do this next one because something a little bit different is going to happen. Sine squared theta equals 4 minus 2 cosine squared theta. Looks like a reasonable problem, but I'm telling you something different is going to happen in this one. Let's try to rearrange some stuff. I don't know. I see a sine squared and a cosine squared, and I'm thinking if I get those both on the same side of the equation, that might be nice. So I'm going to rearrange by subtracting, or no, actually adding 2 cosine squared theta, and then the right-hand side is just 4. This gives me an idea. You know sine squared plus cosine squared equals 1. But this has a 2 out front, right? So that 2 is like getting in the way. How about this? Let's rewrite this as sine squared theta plus 2 cosine squared theta is just cosine squared theta plus another cosine squared theta. Right? All I did was like take this. 2 cosine squared theta is just 2 of them. Okay. And then I did that because I know that this stuff adds up to just 1 by the trig identity. So I get 1 plus cosine squared theta equals 4. Interesting. So my last line here, that's what we're at, and that's equivalent to the original problem. And it's kind of cool because we got rid of sine, and now the problem is just entirely in terms of cosine. We could also subtract 1 from both sides, make it cosine squared theta equals 3. So we've made it a lot simpler by using a trig identity and by splitting up the 2 cosine squared into the 2 pieces. Let's take the square root of both sides. Plus or minus square root of 3. Oh, wait, hold on. I took a square root of both sides, but I didn't do it on both sides. Let's fix that. Use some white out here. I need to get rid of a little 2 here. Okay. There, we took the square root of both sides. Perfect. So square root of the left-hand side, square root of the right-hand side gets a plus or minus. And now we need to figure out places on the unit circle where cosine of theta equals either plus the square root of 3 or minus the square root of 3. Do we know any angles where that happens? I claim that this can never happen. There is nowhere on the unit circle where cosine of theta equals the square root of 3. So how do I know that? First of all, cosine is the x-coordinate of a terminal point. So the square root of 3 is approximately 1.7. Now, you don't have to know exactly what the square root of 3 is, but you can tell that it's greater than 1, right? Square root of 3 has to be greater than 1. So, does cosine of theta ever get greater than 1? Or does it ever get down to negative 1.7? No, there's nowhere on the unit circle where this happens. Another way you could see it, instead of the unit circle, is you could think about the graph of cosine. Waves up and down. The highest it ever goes is a height of 1. The lowest it ever goes is negative 1. It never gets to a height of square root of 3 or negative square root of 3. So what's going on in this problem? What do we have to do now? Well, the answer is there are no solutions. We reached a dead end. We reached an impossible equation. So we just say that there are no solutions to this. And that is something that can happen. You could have a problem that has no solutions. We couldn't really tell by looking at the original equation. It looked reasonable to me. But in the end, that's an impossible equation. All right, so that is the end of our lesson on more trigonometric equations. And in fact, that's kind of the end of the trigonometric equations part. So we had 2 lessons about this. But, you know, in this lesson, we did a lot of examples. So I think we've learned how to do a lot of problems. Now, we are almost at the end of trigonometry. We've got one more video lesson coming up with some extra topics about trig. And then after that, we'll be moving on to another area of pre-calculus, because there is more to pre-calculus than just trigonometry. So you've got that to look forward to. But until then, I hope everybody's doing well, and I'll see you soon. Bye.